Okay. So, actually, I'm going to double back. So within chapter, what are we, 19? Those three reducing agents are the big ones that you need to remember. And it's recognizing how they differ from each other. Because it's ultimately the reason why they differ is why you would use one over another. So the big difference is, again, KOH is a base, H plus HCl. So our Wolff-Kitchener, or the hydrazine, or the N2H4 reaction in the upper left, is the only one that runs under basic conditions. The other ones run under acidic conditions. So if we have functional groups that are acid or base sensitive, we have to be able to adjust our conditions around those functional groups. After that, other things to acknowledge. You have the dithiol in that bottom one where we're using a Raney nickel reduction. That dithiol is a strong nucleophile. And hydrazine is a nucleophile. So if we have multiple electrophilic sites in our molecule, we need to be careful about using either of those reagents because the nucleophile could attack those other positions. Whereas if we take a look at the other one, we don't have a nucleophile or electrophile, at least not a strong one. Okay? Kind of makes sense? So when you look at your structure, evaluate what things are present, what other things could be concerning. If all you're trying to do is remove a carbonyl, reduce it all the way down to the alkane, any one of these is fine. The issue is if there's other functional groups present, now you have to watch out and be careful about your choice. Make sense? Okay. Totally random section for this. I apologize for the order on the slides here. This is our selectivity argument, which is something they keep talking about in chapter 18, because depending on our conditions, we'll select one thing or another. This plays a really big role, because what are we looking at? We're looking at running what type of reaction first? Step one in both of these cases is what type of reaction? It's an acid-base reaction. Step one is acid-base. Step two, what is step two? Substitution. It's a substitution. Which type of substitution? SN2. We're running an SN2. Okay. Does everybody see that? And you're like, yeah, that was obvious. You didn't need to break that down. Really? Oh, okay. Well, you want to see it. Thank you. All right. So if we look at just step one, here's how we're going to do it. So step one. So step one, because I'm aimed at the bottom, I'm going to go to the bottom first. We're going to remove the acidic hydrogen from the tertiary position. Okay. That'll end up forming that enolate, okay, which has resonance stabilization. Okay, like so. Which of those two Lewis structures is the best Lewis structure? Left or right? It's going to be the left. Why the left? The negative charge is on the oxygen. Which of those two Lewis structures dictates the chemistry of that molecule? Now the right one. Okay? So the best Lewis structure is the most stable. That's not the one that's going to react. The one that's going to react is going to be your least best, not even your least, your best worst. Yeah, there we go. Best worst Lewis structure. So in this case, that is our best worst Lewis structure, which then means we have a nucleophile at that carbon that can go out and attack, what are we looking at? CH3I. CH3I and a backside attack. How do we know it's a simultaneous reaction and not stepwise? What was that, Wyatt? So the substrate, where the chemistry happening, the substrate is actually technically not primary, because for it to be primary, it would have to be bonded to a carbon. It's not bonded to any carbons. I would argue that's zeroary, but you know, chemists actually call that methyl. Zeroary is cooler. Okay. A zeroary or a methyl substrate favors SN2 because we can't form a carbocation. Methyl carbocation is not particularly stable. Okay. So the substrate suggests SN2. What else suggests SN2?
Strong nucleophile.
This is a strong nucleophile. How do we know it's strong?
Negative carbon.
We have that negative charge. So there's two aspects of that that suggest we're doing an SN2 type reaction. Okay. When we draw out that result, we might say, well, how is that different from the other system? Well, the other system, if we go through and run that one, what happens? Well, we end up removing, say, the purple hydrogen. Why would we remove the other hydrogen? Okay. There's a steric hindrance aspect to this, but I would make an argument that we shouldn't be looking at steric hindrance. What should we be looking at?
Kinetics versus thermodynamic.
Kinetic versus thermodynamic. And if we look at the kinetics versus thermodynamics, okay, both of those pathways, both purple and red as far as our enolates go, are valid, are viable potential options, okay, under both these conditions. Geez, what is going on with that first structure? It's not uploading right. Yeah, I just can't see it on my screen. Okay. I think we got that right now. Okay. Both of those, purple and red, are viable enolates. Okay. If we had to choose between those two enolates, the red is more valid because I don't accept tertiary. What's the best structure? Left or right? Let's put a box around it. So we can put a box around it for the red one, and we can put a box around it for the purple one. Okay. What are we evaluating to decide kinetic or thermodynamic? Stability. So we need to look for the most reactive thing. What's the most reactive thing in both those boxes? The negative charge. Okay, the negative charge is absolutely the most reactive thing, but it's the same. So we look for the next most reactive thing. Now those of you saying pi bond, yes. Now we look at the pi bond. What is the difference in the location between the pi bonds? More substituted versus less substituted. The more substituted makes it thermodynamically more stable. The red one is a thermodynamic product. The purple one is a kinetic. We can favor the kinetic or the thermodynamic by adding a different base. The base selects which enolate we form. There's our selectivity. Make sense? Okay. If we continue through with the top one, our purple one, I think I see a question over there, Wyatt. I'll be right back with you.
Is there hindrance to the kinetic product, or vice versa, kinetic product will give you?
Yes and no. I would rather you look at the electronic effects before you look at your steric effects. So the electronic effects are going to be the larger driver here. So both contribute to get you to the same result. Okay. We're still running an SN2, backside attack, all that fun stuff, and we end up putting the methyl group on the other position. God, that looks like a lot of stuff up there. Okay. Does it all kind of make sense? See where all the pieces fall and all that fun stuff. Okay. So in this case, sterics and the electronics go hand in hand. Electronics tends to drive reactions. Look to your electronic effects first, just like you would look to charge before you looked at atom effects. Okay? Makes sense? So our selectivity, the base selects. Okay? Just like with our reducing agents, depending on what other things are present, we would choose one over the other. Okay? Synthesis of propylbenzene. Let's do it. 8 or fewer carbons. How can we do this? You want to do this right now, or you want to do this in a little bit, where you can get a little bit more practice with it? Because I can think of at least 2 ways to do it. 3. Maybe 4. Yeah, I think I can get 4 out of that. Okay, let's hold off on that. We'll come back to it. So the reverses are oxidations. The oxidations that you're really responsible for, there's really only one, chromic acid. You see chromium, oxidize. Okay, just do it. The question becomes, how much do you oxidize? Right? Well, is it politically correct chromium? If it's politically correct, you can only go to a carbonyl, period, done. That's it. If you are already at a carbonyl, you can't do anything to it. It's over. It's already done what it can. Okay? Chromic acid, on the other hand, without being politically correct, can oxidize anything it touches. Okay? Believe it or not, it can even oxidize alkenes, though the conditions need to get really, really nasty to force that to happen. So typically, chromic acid is just useful to oxidize alcohols to your carbonyl compounds. Okay? To do an oxidation, you have to have a hydrogen to be able to remove. Okay? Remember, the hydrogen that we're removing is not on the alcohol. That is not the hydrogen we're talking about. We're talking about the hydrogens attached to the carbon, because that's where the oxidation reaction is happening, is at that carbon. The oxygen does not change its oxidation state in the course of this reaction. Why would oxygen not change its oxidation state? Interestingly enough, under most conditions, oxygen does not change its oxidation state. In most conditions, oxygen stays exactly the same. Why would oxygen not change? What is oxidation state? If it makes you feel better, I just yelled at my 130 students about oxidation state and said it's a really hard concept that most people screw up. Probably even me. Now with that segue, what is oxidation state? What is charge?
Number of electrons that an atom has minus the number of protons.
Not quite. Charge is the balance of protons and electrons on an atom. Okay? Technically, that's not true. The charge is the balance of electrons versus our protons across a molecule. And at any given point, do we have an excess of electrons building up, okay, across the molecule? Could the molecule be a single atom? Yeah. Okay. And under those circumstances, the oxidation state and the charge are identical. The oxidation state is the balance of electrons and protons on an atom, not across a molecule. And that's where it becomes confusing, as everybody starts to conflate, if that's the right word. Mix the two words up. It's just a fancy word, right? It sounded cool. Okay? Confuse those two topics for each other, okay? Because they're both looking at how electrons are distributed, okay, around some given target. But the oxidation state is specifically an atom. Charge is across a molecule, okay, where it could build up near an atom. So why then would oxygen always carry the same charge, aka oxidation state? It's always carrying the same charge. It always has the same number of electrons around it, regardless of its situation. Why would oxygen always attract those electrons to be around it?
It's one of the most electronegative.
It's the second most electronegative element on the periodic table. There are only two cases where oxygen does not have the same oxidation state. When it's bonded to fluorine and when it's bonded to oxygen. Every other case, it's a negative 2. Right? And it goes back to electronegativity and that kind of balance. That was a fun 130 segue. I completely lost track of where I was going with that. I apologize. 2 reagents you need to memorize: chromic acid and PCC. Okay? The difference between PCC and chromic acid is ultimately your solvent. PCC is pyridinium chlorochromate. Really all we're saying is that we took the chromic acid molecule and we put it, instead of in water, we put it in pyridine. Because it is acidic, it protonates some of the pyridine, and that's why you get the pyridinium. Okay? Pyridine is simply pyridinium, rolling eraser, without the hydrogen. We now have pyridine. Pyridine has that lone pair of electrons. If we're in an acidic environment, it picks up that hydrogen very quickly, right? And we would be protonated. Okay? What is the difference between those two structures?
Both can act as an acid.
Both can potentially act as an acid. So that's cool. Is that a difference?
Oh, sorry.
Dang it.
Oh,
They are both acting as acids, yes. So they are both similar because they can act as acids, which is why their chemistry still works out very similar and they can both work to oxidize. Why are they different?
One's more nucleophilic.
Yes. Why is one more nucleophilic?
Electronegativity between oxygen and nitrogen.
So if we look at the electronegativity difference between oxygen and nitrogen, I like where you're going with this. Nitrogen is less electronegative than oxygen, which means it is
Less likely to give up, or more likely to give up.
it's more likely to give up electrons, so we would expect the nitrogen to be more nucleophilic than the oxygen. Do we have a nucleophilic nitrogen? Ooh, interesting. We don't have a nucleophilic nitrogen because we're in an acidic environment. We've lost the lone pair. Okay? So I like where you went. Unfortunately, you looked at the neutral structures and not the charged species that's present. So what does that mean? Water is a nucleophile. Pyridinium is not. Okay? Not even acid-base, anything. It's not a nucleophile. Okay? And where does that become relevant? Well, if we go to the mechanism behind these, okay, and this is a general mechanism, it's not perfect. Okay? Our lone pair electrons from the oxygen can attack. We eventually kick out water through a sequence of steps. Okay? And we would have the chromate ester. Why would we call it a chromate ester? Why would we call it chromate? Because it has chromium. Why do we call it an ester? We have an ester. Okay, so it's a chromate ester. The chromate ester is where our chemistry kind of occurs. Our base, be it water or pyridine, will come in, remove the hydrogen, form the pi bond, and we can kick out then the chromium structure, or chromium trioxide. That gets us an aldehyde. So both PCC and chromic acid move all the way through this. There is no differential between them. Right? The real difference comes in the next step. We now have an aldehyde, and what can you tell me about the aldehyde functional group? It has a carbonyl. Keep going.
The carbon can act as an electrophile.
The carbon is electrophilic, which is going to be the important one, so I'll leave that one alone. I won't erase that one later. Okay. What else is special about that aldehyde functional group?
Has a hydrogen. Has another hydrogen that can.
It has an alpha hydrogen. Yeah. What is special about the alpha hydrogen? We have an acidic alpha hydrogen. Because it is acidic, what could potentially happen? We could remove that hydrogen and I would have extra electrons, which I could then attack another carbonyl and do a nucleophilic addition. So we'd have that acidic hydrogen can convert this structure into a nucleophile. Okay? We have to remove it, but it could convert it into a nucleophile. What else do we see as chemistry? What's that? Oh, I totally thought you said the answer.
That's what I said.
What's that?
I said always, the oxygen's always going to be possible chemistry.
Okay, what is that chemistry? Yes.
The lone pairs.
Lone pairs, yes.
Plus couldn't you-
It could attack something. I need a little bit more than that.
couldn't you possibly have resonance if you did get rid of that acidic hydrogen?
Yeah,
Take those out?
but that's a secondary system. We're saying that oxygen, through its electronegativity and through resonance of the pi bond, can stabilize that acidic hydrogen. You're just providing more evidence for why the hydrogen is acidic. We're on to a different topic now. Why is that oxygen reactive? It has electrons. What can we do with those electrons? We could create a bond with anything positive. That's where we have a slight difference in pathways. No, not anything positive. It could share them with a hydrogen, meaning the electrons or that oxygen becomes a base. It will not share them with a carbon. Okay? That oxygen is not nucleophilic. Okay? It will act almost exclusively as a base. So don't try and do any nucleophilic chemistry around that oxygen. Okay? So we've now addressed all of the chemistry around that carbonyl. Anytime we see a carbonyl, we should be thinking of all of those functionalities and all of those reactivities, which then means we would move to the rest of our system, and we now have water, and we have pyridinium to look at. Well, what chemistry does pyridinium have? Positive charge on nitrogen, making that nitrogen act, or that structure act as? Fishing for electrophile, and unfortunately, no. It's going to act as an acid. It can't act as an electrophile, because to act as an electrophile, electrons must share with that nitrogen. Nitrogen already has its octet. That's not happening. That's a bad move. So that will act as an acid. So it could possibly protonate that basic oxygen, making the electrophilic site on the aldehyde even more electrophilic. Is there anything really nucleophilic at that point? We're kind of dead in the water. So yay, we can protonate it, and that's it. Okay? What happens with water? Well, is water as acidic? No. What does water have? Lone pairs. What could it do with those lone pairs? It could share those, because it could act as a nucleophile, sharing those electrons with, say, the electrophile. Generating, after a few steps, what form of a structure? Close. It's not a hemiacetal. For it to be a hemiacetal, one of those H's has to be an R group. Acetal means both of those H's are R groups. It's the hydrate. The change is we added OH and NH. All we've added was water across the structure. That's why it's a hydrate. What is the extra bonus of this new structure? We have a somewhat stable alcohol. What can that somewhat stable alcohol do? Attack a chromium. Okay. Even if we'd protonated with the pyridine, that carbonyl, we would have an OH, but now that oxygen is even worse as a nucleophile. and it can never attack the chromate. Which then means with pyridine, nothing happens. We stop at the aldehyde. But as soon as water is added to that solution, I can make a hydrate. The hydrate now has an alcohol. The alcohol can now attack the chromate ester and can initiate that whole cascade of reactions we just saw again to take us all the way down to the carboxylic acid. Okay? As long as there's a hydrogen to remove. Okay? So that's our oxidation summary. Chromic acid. Notice there's like 50 ways to draw a chromic acid. Yes, it sucks. If you see chromium, oxidize. All of those are chromium. PCC, you might have to memorize as an acronym, as PCC, and realize that PCC is chromium oxidized, but only do it gently. Okay? Make sense? Protecting groups. Okay, we talked about protecting groups. Why are protecting groups generally frowned upon? It's not green. So that's the big blanket boof statement. Drill into that. Why is it not green? Okay, so what they're trying to show here is I'm moving from point 1 to point 2. But to get from point 1 to point 2, I can't go point 1 to point 2. I have to go 1 to A, and then I can go A to B, and then I can go B to 2.
It's not green, but you're more wasteful steps. You might just go from 1 to 2.
Steps 1 and 3 are doing the opposite of each other. I'm adding a bunch of extra chemicals to put something on, and then I'm adding a bunch of extra chemicals to take that same thing that I just put on, take it off, okay, to get me to where I want it to be. Okay? So that's wasteful of the chemicals, okay, which is then wasteful of your time. That's wasteful of the money for the person that you're paying to do this. Right? That is wasteful because every chemical reaction generates waste, which you then have to pay somebody to take care of. So protecting group chemistry is super important if it's needed. Okay? But the idea behind green chemistry is, say, I'm not going to do protecting groups. I'm going to think better about the synthesis to prevent the need to use protecting groups. Okay? So I'm going to change how functional groups are added to the structure to minimize those issues. Okay? We've already seen a protecting group. Let's see, I don't think it's on the next slide. Oh, it is. Look at that. We saw a protecting group with our acetals. The acetals are a classic example of protecting groups. That's the one I really expect you to remember. Okay? For a couple reasons. One, your textbook talks about it as a protecting group. 2, when do we see acetals? When do I ever make an acetal? If I have a carbonyl and I want to turn this into an acetal, when am I going to be able to do that?
Need alcohol.
I would need alcohols. Okay, that's fine. Okay, has to be acidic. Remember the basic conditions favor an SN2. We can't run the SN2 because it's sterically hindered. What else? Or said another way, with the reaction I've got shown up there, would I make that acetal? In red. Top of the screen, underneath ethylene glycol. Is that red reaction arrow valid? Cass, you're shaking your head no. Why are you saying no?
I don't really fully remember, but I remember reading about it.
Because Mike would never ask a question like that unless the answer was no. Yeah. Yes, we talked about it. It is an equilibrium reaction that heavily favors the reactants. Heavily. Why does it heavily favor the reactants? To get this reaction to run, I need HOR HOR plus my carbonyl, and I would be producing H2O. Why would the reaction favor the reactants?
Entropy is one reason.
Entropy is the biggest reason that we can look at quickly and easily here. 3 molecules to 2. Entropy favors more molecules. The reactants are favored. Okay? The only other way we can get our products favored is if we make our carbonyl reactive enough by making it, say, an aldehyde. Okay? So ketones don't form acetals well. Okay? We almost always favor the reactants. Okay? Entropy favors those. How can I make sure entropy is a non-starter issue?
Math.
What's that?
If it was a math problem instead of
I think you're saying change the ketone to something else?
yeah.
Yeah. So that's a possibility, but that's changing the electronics behind this. I don't want to change the electronics. I want to protect a ketone. How can I make sure my ketone is protected? Because if we take a look at the one below, they're showing that I can protect a ketone. But we just said up above, that ain't going to happen. What is different about what I've drawn above versus what they have drawn below? Your alcohols are in one molecule, which means 2 to 2. What does entropy say? I don't care. Do whatever you want to do. Okay? So how can I, now that I've gotten rid of the entropy issue, favor the product formation? I can remove water from my products. By removing the water, that's now going to force the equilibrium to shift towards the products to account for that. What else could I do? Add
H2O.
I add H2O, I'm going to do the opposite. It's going to force the reverse reaction. I don't want to force the reverse. I want to make the acetal. Add an excess of one of the reagents, according to Le Chatelier's principle. Okay. So we're taking advantage of those principles from 152 to force the reaction to occur. So when we're talking about our protecting groups and our acetals, there's really only 2 places they show up. Number 1, cyclic acetals. That's when you get an acetal. Okay? That's when they become synthetically useful, is when we have cyclic acetals. Other than that, they're pretty useless, and it's only just a, do you recognize this as an acetal? I can't make it, but do you recognize it's an acetal? Okay? That's what you want out of the acetal section. The secondary part for our acetals becomes much more relevant for biochemistry. When else do we see acetals? Begins with a C or S, depending on what word you're trying to spell. So S, C, oh crap. Carbohydrates. I still have the right lines. What's the other one? It's the same thing. Sugar. I got the R that time. Okay. If you're looking at carbohydrate chemistry, it's all about acetals. Okay. You take it a step further, for those of you that move into biochemistry, there's 2 common forms of our carbohydrates. And they're all centered on our aldehydes. And we get anomeric positions, and they'll talk about alpha sugars and beta sugars. Does that sort of ring any bells? Okay. What are they talking about, alpha and beta sugars? A carbonyl, when we do an addition, produces 2 products. Biochem just decided to name those two products. One is alpha, one is beta. Okay? That's all they were doing, is naming them. Why is that particularly relevant? Those two forms have very different chemistry. Alpha carbohydrate, oh shoot, I don't remember them now. One of them is used for energy, one of them is used for structure. Okay? All it is a different attack on the carbonyl. And yet one is energy and one is structure. Really subtle difference. Okay? Are those different? I mean, one's structure, one's energy. Like, would I really expect that much of a difference between those? Like, that's not that big of a deal, right? Imagine your structure being used as energy. Oh, I'm hungry. There goes my bones. Okay? Structure's pretty important. I want to make sure structure is very different than energy. And guess what that difference centers on? Everybody's favorite, chair conformations. Yeah. Your biochemistry teacher may not actually tell you that. I only recently clocked that, by the way, for the record. Because I'm recording this. If I wasn't recording this, I wouldn't put that on there. Okay. But in any case, biochem, organic chem, same difference. Okay, so in any case, acetals, protecting groups. Okay. Let's ignore the retrosynthesis. What if we had a different functional group, like an alcohol? I want to protect an alcohol. Are there things that we could put onto alcohols that we could also remove? Yes, that's why we're in this section. What are those things? All the things. These are all the things that you could potentially do to alcohols to protect them. Okay? Remember, one of the key characteristics behind our protecting groups is not just changing the functional group. I can make an aldehyde or a carbonyl or an alcohol an aldehyde. Okay? But if I can't get the alcohol back, that defeats the purpose of the process. Okay? So these as protecting groups, and don't panic about writing these down, I just want you to be kind of aware of them. These can all be used as protecting groups as one form or another. You end up changing the structure slightly, and then that reaction can quickly be reversed. I think on the next slide. No, you're just showing more protecting groups for alcohols. Okay? So there's a variety of things out there. If you ever did synthesis, which it sounds like none of you will, but if you ever did synthesis, you would need potentially to use protecting groups. There's just a list of them that you would then try and play with. Why would you choose one protecting group over another? What do you mean different chemistry? Potentially.
Or the reversibility of it.
Could look at reversibility.
The conditions.
It's probably conditions. If we take a look at 4, we needed an acid. If we look at the other one, we're not looking at acids to reverse that. Okay? So changing the conditions under which you put the protecting group on could have an effect on the rest of your structure. Because remember, the only reason you're using protecting groups is because you have a crap ton of functional groups. Each of those functional groups has their chemistries that could potentially affect one another. Okay? So with that, let's do, where'd it go? It was back here. That guy. Okay. We have to use a carbon-carbon bond formation. How could we possibly do this? All right, well, which bond do you want to make? I agree, let's make that last one. Let's make this one. Because our rule was 8 or fewer carbons. There's 6 here, 7, 8. So I need to make that bond. Okay. So if I cleave this, I would end up with this guy. And then CH3. Okay. Well, to figure out what my reagents are, I'm going to have to deal with charges, right? Okay. Well, so I could either have this one be negative and this one be positive, or the other way around, right? Okay, well, what happens if I do negative and positive like that? Okay. primary carbocations, not likely to form. So I could do this as a straight substitution, right? If I had a strong nucleophile, if that was very, very negative. Okay. How could I make that position negative? So we go through and say this guy needs to have bromine on it. So it's now a positive carbon, right? Everybody see that? How can I get that carbon now to be negative? So carbon would have to take electrons from something. What do you got, Waleed? Look like you started to say something.
Anything that's like irreversible, that would be maybe a
Okay. Trying to turn it into a Grignard. Okay, so we could potentially try, whoops, do something like that. And just say this is now a straight Grignard reagent. MGBR, is that what you're suggesting? Okay. Sure, that seems reasonable. How would we make the Grignard? Well, we take that back one step. That needs to be a bromine, and I react that with magnesium. Okay. Then we could try and do that. The issue is that Grignards tend to favor attacking carbonyls more so than alkyl halides, but we could try that. Is there another way? How else could I make that carbon negative? Huh? Okay, so we're going straight at the let's just make it negative outright. Is there another way we could do it without bringing in a metal? Yes, yes there is. What do you mean double bond? Well, I think carbon, keep freaking doing that, could potentially remove electrons from a hydrogen, but then that negative would have to be resonance stabilized to exist. So what if I did this? Oh, there we go. Okay. But that would mean I'd have a carbonyl. So yeah, this would work, and this would potentially get me my linkage. I do my acid-base step, followed by my substitution. And then I have a carbonyl on there. Huh. How do I get rid of a carbonyl? Oh, we could do a reduction with, say, the Wolff-Kitchener, if we had happened to memorize that as a name, which was our N2H4, our KOH, and then really heat. The rest of it, triethylene glycol, H2O, kind of afterthoughts, but the N2H4 and the KOH. Okay, so that could work. Okay, what else could we do? What if? Well, we had those, but then I did, oh, pH3, would that work? That would be the pH3 thing, and then we have that lithium base, which, of course, being lazy, we'll just write lithium base. Gets me my negative carbon, but then that would have to attack a carbonyl, and I was drawing an alkyl halide, so maybe let's change that instead to a carbonyl, and we made that like that. Well, that would add that extra carbon, but that would then mean I have a double bond out there, right? Well, I don't want a double bond. Can I get rid of that double bond? Yeah, how can I get rid of that double bond? Hydrogen gas and platinum. Oh, so we could do a Wittig. We could do a Grignard. We could do the alpha hydrogen off of a carbonyl. Okay, makes sense? So there's lots of different routes. What you need to be doing is kind of poking at them and seeing what happens. When it comes to the ACS with something like this, what they would probably do, or I would do on, say, maybe a future exam, is list 4 syntheses with all those reactions. Say, which of those get you your product? You need to go through each of those steps and be like, this is how it would work. Right? So, is that an easier question than this? Yes. Why is that an easier question than this? I'm giving you all the pieces. You do have to know what those pieces match to and how that chemistry works, but you don't have to come up with it on your own. Okay? So that ultimate goal of synthesis or retrosynthesis and coming up with all the reagents, yes, we need to be pushing at that. But don't freak out if you aren't there. Look at your multiple choice, take advantage of that information to help kind of needle your way through. Okay? Because you have an exam, you have the whole exam with lots of information in it. Okay? A synthesis question may be at the very beginning. That may be a really hard question for you to answer. But maybe if you go into the multiple choice, you realize that you can do a conversion from the multiple choice and go, oh, I can take an alcohol and turn it into a carbonyl. Well, I'm going to put that up here as a reagent for my synthesis. I don't know what else to do with it, but hey, at least I can do that. Cool, that's fine. Maybe that's a productive step. Maybe it's not. Okay? But by moving those pieces in there and starting to shift in that direction, you can see it. It's those carbon-carbon bonds that are tricky to make. Okay? But you're looking at a relatively limited pool of reagents. Okay? Grignards, we can look at Gilman. Could we do Gilman on this? No, we don't have enough carbons because we have to have 4 carbons do the alpha beta, unsaturated, right? So we wouldn't be able to pull that off.
Another question about H2 and platinum. Does that not reduce the
That will not touch the benzene, and that's because the benzene is not an alkene. Okay. So we can reduce benzene. And officially it is shown up in slides. We will talk about it in a lot more detail. What is the reagent that allows us to reduce benzene?
Acid,
What?
chromic acid.
Chromic acid does not reduce it, it actually oxidizes it. And we haven't talked about that. I don't even remember if the textbook has talked about that. Whoops. But we will talk about that. That one I've always found frustrating, personally. Oh. Yeah, chromic acid doesn't care about my feelings. Let's make sure I do this right. I think that's right. We could do this reduction. We can't just reduce a single double bond out of it perfectly and leave the other two conjugated. To do the full reduction, you have to completely unconjugate the whole system. What reagent did this? I know, it's a stretch. Sort of, yes. It helped us synthesize a trans alkene. Solid sodium in the presence of ammonia will reduce an alkyne to the trans alkene. It will also reduce a benzene ring down to whatever the heck you want to call that structure, a cyclohexadiene. Okay. That's the Birch reduction. Okay. I know, well, we went through it really, really fast, so I don't expect you to know that one yet. That is the very end of the semester. We'll talk about that one again. Okay. So yeah, reducing aromatics or benzene rings officially, not easy. You need very particular chemistry. Sodium metal is pretty nasty.
solid reduction we talked about?
Won't touch it. Rainy nickel can mess with it, I think. I have to look that one up. Rainy nickel is a violent reducing agent.
But as far as where we're at, right?
As far as where you're at, don't worry about it. Okay? So questions about that? Should we move on to the last slide, or the next to last slide? You would all know that that's a joke, right? Because you downloaded the slideshow to realize we've already talked about the last slide. Where do you have questions? Thank you, Lisa. Where do you have questions? Anything. The pieces up there. So you were given the synthesis roughly outlined, that you were starting with this carbonyl compound. It was reacted with something followed by CH3Br to make a product A. Okay? That product A then has the spectroscopy shown, which I might need to go back and look at a little bit. Okay, so we have our IR, obviously, and our HNMR, obviously, that we then need to go through and interpret. I'm fairly certain that there must be some kind of typo because I think I provided more context of what information was in there, and I don't know why that didn't show up. Okay. If it wasn't a typo, then I've provided more context on what those are. So let's start with the IR. What do we see in the IR? So we have some signals here of CH, SP3, and then we have C double bond O at 1700. Right there, 2 points. Yay! Right? So show work. Right? It's expected of you, so put that information down. Okay? Then we've got our HNMR to help us out. Okay? Which is pretty awesome. I did a fantastic job drawing all that spectra. So the ACS kind of does this to you as well. They're a little bit cleaner about it. I'll fix whatever that peak number is in a second. So let's try and go through and evaluate this. So we have 3 groups of signals. So we'll call it red, we'll call it blue, and we'll call it purple. Okay. The red signal and the blue signal are roughly the same height, right?
Yeah.
Okay. But the red signal has 2 peaks. What does that mean? Okay. So when we're looking at our NMR, we've got multiple things to evaluate. The number of signals, so we could jump to that. We've got 3 signals. Right? Everybody's good with 3 signals? Okay, so let's see what we can do with that information. So we have our starting material, carbonyl, and then we know we're somehow adding CH3Br. Well, CH3Br has what chemistry? It's an electrophile. That carbon is positively charged because the bromine is a leaving group. Which means my now Christmas colored ketone needs to be a nucleophile to share electrons. So where's the most nucleophilic site in that carbonyl? Oh, we just talked about this. What do we need to do? We need to get rid of an alpha hydrogen. The oxygen can't act as a nucleophile. We have to remove an alpha hydrogen. Why is that problematic? There are 2 alpha hydrogens. So I get 2 possible answers. I could have formed a negative charge on the outside, or I could have formed the negative charge on the inside. Okay. One of those being the kinetic product, the other one being the thermodynamic. What would dictate which of those I made? The base, the choice of whatever B was. Interesting choice of letter. Okay? So we have to figure out what B was. Okay, well, we know we have 3 signals, so let's just propagate this out. CH3 is then reacted with both of these, or potentially both of these. And we'd put a CH3 over here, right? There's my Christmas colored piece and my methyl. And then, because I've already started doing it, let's just continue with my stupid Christmas color. right? Those are my two possible products, where the top one is my kinetic product and the bottom one is my thermodynamic product, right? How many signals are in the kinetic product? You started mouthing it. Almost started mouthing it. There's hydrogens here, there's hydrogens here, there's hydrogens over here, and here. Due to symmetry, these two are the same, these two are the same, there's two signals. What does that mean? It's not the kinetic product. Okay? Let's verify, make sure we didn't screw something up. Let's take a look at the thermodynamic. There's 1, there's 2, there's 3, ooh, snap, there's 4.
3 and 4 would be
The 3 and the 4 are the same due to symmetry through the middle of that. There's only 3 signals.
would the 3 and 4 be showing up at 1?
We're going to address that next part. So, we know that answer A is the thermodynamic product. What does that mean our base needs to be?
Stupidly strong. No?
Not, and so you're going back to bulk. We can't deal with bulk. We have two choices of base, stupid strong or just strong. Stupid strong needs to do what? Die as fast as possible. And get rid of the stupid, no, that's not what I mean. Let's not do that. Okay. Get rid of the stupidly active things first. So I'm going to do that as fast as possible. So stupid strong means kinetic. I want thermodynamic. I don't want stupid strong. I just want strong. What's my strong? Okay. A negative oxygen, the classic one to go with is T-butoxide, okay, which we could draw as our little spider fingers or whatever you want to call that. Okay. Or we could write that out as T-butoxide. In this respect, I've answered the IR. I've answered the thermodynamic product for A. I've answered what the base is for B. I've put some information down for the NMR, but I said, hell no, I can't figure it out. Cool. You probably got 80% of the points, if not 90% of the points. Okay? So use what knowledge you have to build and scaffold. Okay? Is everybody okay with everything that was shown up there? Okay, because now I got to clean this up to actually look at the spectroscopy, the NMR. Okay, so let's get all that cleaned away. So in our NMR, I love how it wasn't perfectly white to begin with. Okay, so we had 3 signals. Let's take a look at the red one. So our red signal shows up with a chemical shift about 1. What does that give us as far as information? It's probably an alkane. So we're looking at a hydrogen bound to just a carbon. Okay. After that, we have the integration. What is integration? It's a ratio. Okay. Ideally, that would be given to you. That is given to you on this next test. It is not given to you on the final. Okay. So how could we interpret a ratio out of that? Well, the blue versus the red signals are roughly the same height, right? Okay. Except the red signal has 2 peaks. What does that mean about the ratio? 1 to 2. The red signal has twice as many as the blue signal. Make sense? Okay. Purple signal. That looks tiny, right? There is a bunch of little peaks there, though. If we add all those up, what we'll probably end up seeing is that that purple signal is about 1/3 of the height of the blue signal. What does that mean? It's a 1 to 3 ratio. Purple is 1, blue is 3. Purple is 1, blue is 3, which means red is 6. So if I have an integration of 6, what does that mean? I have 6 of those above. What What is the easiest way to get 6 of those above? 2 methyl groups. I do not know what those 2 methyl groups are connected to. I just know that they are identical. Whatever is connected to one is connected to the other. So I'm not connecting them in that space between them. I'm just saying they're there. After integration, what can I move to?
Splitting.
The splitting pattern. I have 2 peaks. Okay, according to my splitting or my multiplicity, okay, number of peaks equals the number of neighbors plus 1. So if I have 2 peaks, neighbors plus 1, I have how many neighbors? 1. What does that mean? This is now valid. Do I know that those CHs that I just drew are identical, are the same one? No. I don't really have any context to guarantee that those are the same based off the information I've just looked at. Okay. Can I add a little bit more information from the context of the question to draw some conclusions about that? Yeah, why are you saying that?
Because we know that where it's symmetrical is going.
Okay, so we could go based off of the product that we know already, so we're just trying to match up. Okay, that is a fair game to run, but I would argue you're now looking at the answer, and I'm trying to step back and say, is there context without knowing the answer to get us there?
The 2 peaks. I mean, they're giving off the same signal, so
How many carbons have I drawn? 4. Take a look at my starting material. How many carbons have I drawn? 4, right? My starting material. I add an extra carbon, I'd have 5. Okay? I have accounted for 4 carbons already. I still have 2 more signals to evaluate, which means one of those could potentially add into this. Okay? So that means if those 2 are unique, there has to be 2 CHs. Could I possibly get 2 CHs with one reaction with that structure? That's making your head hurt, I'm guessing, because of the looking down, maybe. Let's avoid that then. Okay. I would argue that we could look at that, but if you can't see it, that's fine. Okay. Those are our pieces from our red signal. So guess what we now do? We repeat that process for the blue signal. The blue signal, our chemical shift showed up about 1.2, which means still probably carbon hydrogen. What was the integration? 3. So I'm looking at a CH3, more than likely. What's its splitting pattern? It only had 1 peak, which means how many neighbors? No neighbors. Just that CH3 all by itself. The IR tells me I also have a carbonyl. I'm going to add that in. How many carbons have I now drawn in, or am I counting up? So red, I have how many carbons? 4. Blue, I have. Blue is only 1 right now. IR tells me I have another one. I have a total of how many carbons? 6. How many carbons could I possibly have in my product? 5. What does that mean? Before I go any further, my spectra is telling me I have too many carbons. What does that mean?
you have to take one out somewhere.
I've duplicated carbons somewhere. Could that blue CH3 be a red CH3? The blue CH3 says no neighbors. The red CH3s have a neighbor. The blue cannot be the red, so that's not duplicated. Can the red be the red? Oh, maybe I just drew that too many times. What's the integration? 6. I have to have 2 red CH3s. I still have to have a carbonyl. What's the only thing left that could have been duplicated? The CHs. Right? And I had to do this condensing because I ran out of space. Okay. So now let's summarize what we've got. Okay, from the red, I have a CH3. CH3. It's telling me I have a hydrogen there yet, but I'm going to put that in black. Why would I put that in black? Because it's not the red signal. The red signal is telling me there's another hydrogen, but I haven't found that hydrogen yet. Okay? I also know, where do we go? That we have a blue CH3. I also know I have a carbonyl. So far, so good? I'm going to have to switch colors here. Let's take a look at our last signal, the purple one. Where does it show up? Two and change. That's starting to drift kind of high. That might be kind of difficult to delineate. So we might just call it a hydrogen bound to something. I don't know what it is. Okay. Its integration, super, super tiny. We're saying it's only one hydrogen. So all I know from the integration, I have a hydrogen bound to something. I don't know. Then I move to the multiplicity. The multiplicity, how many peaks are there? And this is where we got to get our microphone, magnifying glass out and stare down at it. So Cassie's going to tell us a number, and then I'll tell her if she's right or wrong.
I was thinking 4.
I'm not thinking 4. Okay. I see 5. Okay. 5 peaks, which would mean 4 neighbors. That seemed weird. No? Oh, I thought you had. Do I have any positions left that have only 4 neighbors? No, that doesn't quite look right. So let's take a closer look at that. And this is one of those fun things. And yes, sometimes the ACS does this to you too. Oh gosh, my eyes are crossing. You drew a pencil mark there. It might be hitting me too. I don't think it is though. 1, 2, 3, 4, 5, 6. I see at best 6 peaks. Right? And this is where we're going to run into an issue. That still doesn't line up nicely, does it? Okay, so that seems weird to me. So what am I going to do? I'm going to leave it as a question mark. I know there's a hydrogen. I know there's a hydrogen bound to a question mark. And I know that hydrogen has some number of neighbors. So I'll go back to my pieces. Okay, I have 1, 2, there's a carbon, 3, 4, 5. 5 carbons that somehow have to get connected. Okay, how could I possibly connect those? There's only one way to connect them. What does that look like? Yeah? There's my 6 hydrogens. There's my 3 hydrogens. Those fit our pattern. And then what the heck is going on around that hydrogen? Well, the splitting pattern didn't match, but it's also really, really, really tiny. What are the odds we're just not seeing it cleanly? It's possible. So what does that mean? That's my best guess. I move on. I can't evaluate any further. That at least finalizes a structure. That structure has all of the right pieces. The spectroscopy may not line up perfectly, but it's as close as I can possibly get. I'm not going to sit and stare at it longer to try and figure it out. The multiplicity is by far the hardest signal to evaluate, particularly when it gets down into more than 5 or 6 peaks. It becomes very difficult to distinguish those peaks. Don't put a lot of weight in that analysis. Okay? Particularly because you're not very good, and that sounds mean, you're not very good at spectroscopy. Don't put a lot of weight and emphasis behind the hardest part to interpret. That makes no sense. So do the best that you can. You know it has neighbors. According to your structure, does that hydrogen have a bunch of neighbors? Yeah, it's got 6 neighbors. It should split like crazy. Okay? It should split till 7. I see 5, maybe 6 peaks. I mean, ballpark, that's as close as I can get. That's all I got. That's all I've got. Move on. Make sense? Turns out that analysis is correct. This would be one of those cases too, if you're like, I've finished the whole test and I still got 20 minutes left, raise your hand and be like, hey Mike, I can't figure out what's going on with the splitting patterns here. Can you help me out with it? On the final, the answer will be no. On this test, the answer will be, I told you it's right there. That's where it says, that's the splitting pattern. That's a lie, I actually didn't put that on the test. If you have that question, you can ask that question. I put the integration on the test. Okay? Make sense? So, review your spectroscopy, particularly IR. IR is an easy thing to review. Okay? Quick, easy, quick points. Okay? The NMR, a lot more difficult. Where spectroscopy will show up is within the context of another question, so that you can bounce off of both.